Welcome to the Deep Dive.
Great to be diving in.
Today, we're tackling something huge, really foundational. It's about how we build reliable knowledge.
How we figure things out about the world, basically.
Exactly. And we've got a solid stack of sources here, including some really detailed ones focusing on, método científico.
The scientific method.
That's the one. So our mission today is to really unpack these sources.
Dig into them.
Yeah, figure out what exactly is the scientific method according to this material. How does it work step by step?
And maybe why it's considered so important, so fundamental.
Right. It's almost like the operating system for building knowledge we can trust, wouldn't you say?
That's a really good analogy, actually. It's the underlying process, not just facts, but how we get those facts.
Making sure they're solid.
Yeah, built on something sturdy, tested, refined, all that. It's evolved, of course, but the core ideas in these sources are powerful.
I'm really keen to get into the characteristics mentioned. You know, what it is, and just as importantly, what it isn't.
Those distinctions are crucial, definitely. They separate it from other ways of thinking or knowing.
It feels like looking under the hood of discovery itself.
It really is the engine, isn't it? Driving progress. Without this kind of structured approach, well, what are you left with?
Speculation, gut feelings.
Pretty much. Or maybe just accepting things because someone important said so. Dogma. This method offers a way to check against reality.
Okay then, let's jump right in. Starting at the beginning, according to our sources, what is the scientific method at its heart?
Okay, so the sources first emphasize it's a rigorous process. Rigorous is the key word there.
Meaning disciplined, structured.
Yes, exactly. Systematic discipline, not haphazard. And its main goal, its purpose, is to establish relationships.
Relationships? Between what?
Between facts, primarily, but also between those facts and the larger laws or theories that explain why those facts are connected, how the world works.
So it's not just collecting isolated bits of information. It's about seeing the connections, building the bigger picture.
Precisely. Moving from just description to understanding the underlying principles. And the rigor. Well, that comes from how it generates this understanding. The sources really stress this. Its ultimate aim, its finality, is generating scientific knowledge through empirical verification.
Empirical verification. Let's pause there. What does that mean exactly? Empirical.
It means relying on evidence you can gather through your senses, or, instruments that extend your senses. Observation and measurement.
Things you can actually see, touch, measure.
Right. And verification is the part where you test or check if something holds true based on that observable evidence.
So empirical verification is confirming ideas by checking them against the real observable world.
You got it. It's the opposite of just, say, accepting something on faith or because it sounds logical in your head. You have to check it against reality.
Makes sense. So a structured way to build understanding by testing ideas against observations. And the sources mentioned a core cycle.
Yes, a fundamental loop that drives it. It starts with careful observation.
Noticing things.
Right. Then, based on those observations, you develop a hypothesis.
A possible explanation.
Yeah.
An educated guess.
A possible explanation, yes. And crucially, it has to be testable. Then comes experimentation.
Where you test the hypothesis.
Exactly. You design ways to see the hypothesis holds up when checked against new observations or controlled conditions. And the results feed back, maybe leading to new observations or refined hypotheses.
Observation, hypothesis, experimentation. That loop, it sounds iterative.
Very much so. It's a constant cycle of idea, test, evidence, refinement. That's what makes it dynamic.
Not just stating a belief and sticking to it.
Definitely not. It's about putting ideas constantly to the test against the empirical world.
Okay, that gives us a solid core definition. Rigorous, empirical, focus on relationships, using that observation hypothesis experiment cycle. Now, about those characteristics, the sources list what it is and what it isn't. Let's dig into those. What's the first defining feature?
The first one highlighted is absolutely central. It is not dogmatic.
Not dogmatic. So it doesn't deal in absolute, unquestionable truths handed down from authority.
Precisely that. The source explains its basis isn't some set of revealed principles you just have to accept. It's based on laws and theories deduced by humans.
Deduced from?
From observation and experimentation. And here's the kicker, the really anti-dogmatic part, according to the source. Its laws are always rejected if facts contradict them.
Always rejected if facts contradict. Wow.
Yeah.
That's huge. It means science has to be willing to be wrong.
It's built into the system. If new evidence, new facts come along that don't fit the current understanding, the understanding must change. The facts take precedence.
Not the belief.
Not the belief, not the theory, not the law. The source says its validity is confirmed by the daily experience of its use.
Meaning, it works.
It works. The laws derived this way allow us to build bridges, make predictions, develop technologies that function. Its validation comes from its practical effectiveness and predictive success in the real world, not from ancient authority or unchanging texts.
So it's constantly being tested just by being used. And if it fails those tests,
It gets revised or thrown out. It's dynamic, self-correcting, fundamentally reliant on evidence.
that really separates it from systems based on fixed dogma, a willingness to discard ideas. That's powerful.
It truly is. And this leads directly into the second characteristic mentioned.
Which is?
It builds by establishing relations between observables, not based on absolute certainties.
Observables again, things we can detect, measure.
Exactly. It focuses on the phenomena and facts we can actually interact with empirically, the things we can see, measure, quantify, and it looks for the relationships between these observable things.
So it stays grounded in what we can actually perceive and test in the physical world.
That's the idea. It contrasts with approaches that might rely on, say, unobservable forces or metaphysical principles that you can't really test empirically.
Okay, so the focus is on observable things and their connections. How does it usually map out those connections?
Well, that brings us to the third characteristic. It normally uses mathematics.
Ah, math. The language of science, as they say.
And for good reason, according to the sources. Math allows for precision and quantification.
Moving beyond just saying, this affects that.
Right. Instead of heat makes this expand, you can use math to say, for every degree Celsius increase, this material expands by exactly this many micrometers. It provides a precise, objective way to describe relationships and make testable predictions.
It takes the fuzziness out, allows for clear models and checks.
Precisely. It helps find patterns, build models, and express relationships in an unambiguous way. Very powerful tool within the method.
Makes sense. Okay, what's the fourth characteristic listed in the source?
This one is stated quite strongly in the source material. It says the scientific method is one with which laws can be obtained that constitute the unique way to guess the future and know the past.
The unique way. That's a bold claim from the source. Not just a way, but the unique way. What's the implication there? What is it contrasting with?
It is a very strong statement. Presenting it as the source does, the idea seems to be that the laws derived through this empirical method have a special kind of power for prediction and explanation regarding the physical world.
How so?
By understanding these empirically verified relationships like gravity or chemical reactions, we can predict what will happen under certain conditions. That's the guess the future bit.
Like predicting an eclipse or how a drug might affect the body.
Exactly. And we can also explain why past events happen based on these laws. That's the know the past part, like understanding geological formations or evolutionary history. The source seems to position this predictive and explanatory power derived from empirical testing as distinct from and perhaps more reliable for understanding the natural world than other methods like, well, maybe divination or explanations based purely on tradition or authority.
So the source is really highlighting the unique effectiveness of this method for making reliable predictions and explanations about the physical world.
That appears to be the thrust of the claim as presented in the material, yes. It emphasizes the practical power derived from its empirical basis.
Interesting phrasing. Okay, and the fifth characteristic.
The fifth is that it deduces laws that nem sempre obedectum au bom senso, which translates to.
Don't always obey common sense.
Right.
How can that be? Isn't common sense usually, well, sensible, based on experience?
It is based on experience, but usually our everyday limited experience. Common sense works well for the scale we live on, but science, through rigorous observation and experiment, sometimes reveals things about the universe that operate on very different scales, or in ways that just seem bizarre from our everyday perspective.
Like things being in two places at once in quantum mechanics.
Yeah.
Or time slowing down at high speeds in relativity. Stuff like that.
Exactly, those kinds of concepts. Our intuition, our common sense, didn't evolve dealing with the quantum realm or near light speeds. So when science investigates those areas, the findings, supported by evidence, can seem deeply counterintuitive.
So common sense is a starting point, maybe, but not the ultimate judge.
According to this characteristic, no. Science follows the empirical evidence wherever it leads, even if it conflicts with our gut feelings or what seems obvious. It challenges our intuitions.
That's a crucial point. Okay, so we have the ice characteristics. Not dogmatic, based on observables, uses math, holds this unique predictive explanatory power according to the source, and can defy common sense. Now, let's flip it. What does the source say the scientific method isn't?
You're right, clearing up misconceptions. First point, it is not a method that establishes laws that are unalterable and are almost never followed.
Okay, unalterable directly contradicts the not dogmatic point. Laws can change.
Absolutely. The source reinforces that scientific understanding evolves. Laws aren't set in stone forever. They are our best current descriptions, subject to revision if new contradictory evidence emerges.
And the almost never followed part. That sounds wrong, too.
Yeah.
Completely wrong, based on how science is applied. Think about engineering, medicine, technology. They all rely fundamentally on applying established scientific laws and principles. These laws are followed constantly because they work reliably within their known limits.
So they're provisional, but also highly reliable in practice. That makes sense. What's the next isn't?
It is not a method that establishes laws based on faith, but which are improbable.
This goes back to empirical verification versus faith.
Exactly. Scientific claims require empirical evidence. Faith, by definition, often operates independently of, or sometimes even counter to, empirical evidence. And while a new scientific hypothesis might seem improbable at first glance, its acceptance depends entirely on whether it survives empirical testing, not on belief or how likely it feels initially.
The evidence decides, not the initial feeling of probability or belief.
That's the core principle. It has to be testable against reality. And the third isn't is very specific. The source states it is not a method that uses magical formulas, special rituals, or chosen human beings born with extraordinary powers that make things happen when invoked.
Wow, that's drawing a very clear line against, well, magic and mysticism.
It is. It directly contrasts the scientific method's reliance on observable phenomena, testable procedures, and universally applicable principles with concepts based on the supernatural, the secret, or unique, inherent personal abilities.
Science is presented as something anyone could theoretically do if they follow the steps, not something requiring special powers.
Precisely. Scientific results should be obtainable by anyone following the same method. Magic, rituals, inherent powers, these usually depend on belief, specific individuals, or mechanisms outside the realm of empirical testing and replication. They're fundamentally incompatible with the open, evidence-based, repeatable nature of science described here.
So these isn't points really sharpen the definition by excluding these other approaches.
They clarify the boundaries and the specific domain of the scientific method, the empirical, testable, natural world.
Right. Okay, we understand its nature now, what it is and isn't. Let's get into the nuts and bolts.
Yeah.
How does someone actually do science, according to these sources? They outline steps, right? Let's walk through that process. Where do we start?
The source breaks it down into 6 main steps, starting with our fundamental interaction with the world. Step 1, observation. Observation.
Yes, looking around.
More than just casual looking. It's becoming aware of phenomena through our senses, often with focused attention, maybe using instruments. It's about noticing patterns, anomalies, regularities, carefully registering what's happening.
Okay, so you observe something, something catches your eye, sparks your interest. Then what?
That leads naturally to step 2. Indução e perguntas. Induction and questions.
Induction. Like seeing a pattern and generalizing.
Sort of. You see repeated instances or a particular striking event, and it makes you wonder. It raises questions about why or how that phenomenon is occurring. Observation sparks curiosity.
Why do apples fall down, not up? How do birds navigate? That kind of thing.
Exactly. Asking questions based on what you've observed. And those questions lead directly to step 3. Hypothesis.
The proposed answer.
Yeah.
The educated guess we talked about.
Yes, the possible explanation for the question you asked. But here's that crucial condition again, emphasized by the source. The hypothesis must be able to be tested empirically.
It has to be falsifiable, in a way, something you can actually check against reality.
Precisely. It can't be just any speculation. It has to be structured so that you can design an experiment or make an observation that could potentially support or refute it.
So Invisible Gremlins divot is out.
Unless you can devise a way to empirically test for invisible gremlins, yes. A testable hypothesis might be something like, this fertilizer will increase crop yield compared to no fertilizer. That's testable.
Okay, you have your testable hypothesis. Next step.
Step 4, experimentation. Experimentation.
Putting the hypothesis to the test.
This is where you actively intervene, manipulate variables if possible, control conditions, and gather data specifically to see if the predictions of your hypothesis hold true. The source stresses testing it a sufficient number of times.
Why sufficient times? Repetition.
Exactly. To ensure the result isn't just a fluke, a one-off, or due to some random error, you need to establish regularity and reliability. Can you get the same result consistently under the same conditions?
Rigorous testing. Repeated. Got it. So you run the experiments, collect the data. What then?
Then comes step 5, demonstration, demonstration, or analysis maybe.
Okay. What happens here?
You analyze the results of your experiments. Does the data support the hypothesis? Does it contradict it? Or are the results unclear, maybe irregular?
So you figure out if your idea worked or not.
Right. And the source points out something important. If the evidence doesn't support the hypothesis, if it cannot be proven true by the experiments, well, that's not failure. It means you can formulate a new hypothesis.
Ah, the iterative cycle again. If your guess was wrong, you learn from that and make a better guess next time.
Exactly. Disproving a hypothesis is still progress. It still adds to knowledge by showing what isn't true. It guides you towards better explanations.
So it's okay to be wrong, as long as you learn from it.
It's essential to the process. Now, what if the hypothesis does hold up? What if repeated experiments consistently support it?
Then you move to the last step.
Yes, step 6, tease, thesis. This happens if the hypothesis is not refuted and is consistently supported across all the tests conducted.
So it survived the trials.
It did. At this point, you draw conclusions based on that strong evidence. And if the hypothesis is significant and robust enough, it can contribute to establishing or refining broader scientific laws or theories.
So a well-tested, consistently supported hypothesis can become part of our larger understanding. That makes sense. Observation, questions, hypothesis, experiment, analysis, conclusion, thesis. That's a clear pathway.
It's the structured process for building that reliable knowledge we talked about.
Okay. Now, underpinning this whole structure, the characteristics, the steps, the source talks about 2 fundamental pillars, like the absolute bedrock foundations. This sounds really crucial.
They are presented as absolutely essential, non-negotiable for scientific validity according to this framework. The first pillar is reproducibility.
Being able to reproduce the results.
Exactly. The capacity for an experiment or observation to be repeated by others. And the source is incredibly emphatic about this.
How so?
It states that scientific publications must include all the necessary data and methodological details so that someone else can replicate the work.
All the details, like a recipe.
Pretty much. Enough information that another competent researcher anywhere in the world could follow your steps and ideally get the same results. And the consequence if you don't provide that.
What happens?
According to the source, if the data and methods aren't shared sufficiently to allow replication, then the work is not considered a scientific experiment. Full stop.
Wow. That's a really high bar. It forces transparency.
It does. It's a core mechanism for verification and building trust. If someone claims a breakthrough but keeps the method secret, how can anyone else check it? How do we know it wasn't an error or bias or worse?
Right. Reproducibility allows for independent checking, peer review in action.
Exactly. If others repeat the experiment and get different results, it calls the original finding into serious question. It's a critical quality control filter. It ensures findings are robust, not just specific to one lab or one time.
So it's not just good practice, it's a defining requirement for the source. Okay, that's reproducibility. What's the second pillar?
The second pillar is refutability. Refutability, or sometimes called falsifiability.
Refutability. The ability to be refuted or proven false.
Precisely. The source states that any scientific hypothesis or claim must be capable, at least in principle, of being proven false through empirical evidence.
You have to be able to imagine some kind of observation or experiment that could show your idea is wrong.
Yes. If there's no conceivable empirical test that could ever contradict your claim, then it falls outside the realm of science according to this principle. The source uses a specific example to make this clear.
What's the example?
It says, if I say all purple cats are females, it is impossible to falsify because no purple cat can be observed.
Okay. Because purple cats don't exist, you can't find one to check if it's male or female. So you can never empirically test the all are females part.
Exactly. The claim is protected from any possible empirical disproof because the subject itself isn't observable. You can't perform the necessary test.
So the claim is untestable in reality.
Correct. And then the source makes a direct link. It says that similar kinds of claims, claims about things that cannot be empirically observed or tested, are sometimes publicly disseminated, using extraterrestrials as an example of often unobservable entities in such claims.
So the source is using the purple cat example to illustrate why claims about things we can't observe or test, while they lack refutability and therefore fall outside this definition of science.
That seems to be the clear implication presented in the source material. Refutability acts as a demarcation criterion. Scientific claims must be vulnerable to being proven wrong by evidence. Non-scientific claims often aren't because they deal with the unobservable or untestable.
And this vulnerability, this ability to be proven wrong, is seen as a strength.
A fundamental strength. It means science is always open to correction by new evidence. It doesn't claim final absolute truth. It's provisional, always ready to improve its understanding when confronted with contradictory facts. That's how it makes progress.
So, reproducibility ensures we can check each other's work and build reliable findings. Refutability ensures our ideas are actually connected to empirical reality and can be corrected by it. Powerful pillars.
They are the cornerstones, according to the source, that ensure the scientific method generates knowledge that is both verifiable and grounded in the observable world.
Okay. We've covered a lot of ground: the definition, the characteristics, what it is and isn't, this step-by-step process, and these two absolutely critical pillars. Let's try to pull this all together now. What does this whole framework, this scientific method, mean for you listening to this? How is it relevant day to day?
Well, synthesizing it all, the scientific method, as laid out in these sources, is this structured, evidence-based, self-correcting way of understanding the world. It starts with observation, forms testable ideas, rigorously checks them against reality through repeatable experiments, and demands that claims are open to being proven wrong.
It's a system designed to filter out error and build reliable knowledge.
Exactly. And its relevance for you, even if you're not a scientist, is immense because you constantly encounter claims about how the world works.
From news, online, everywhere.
Absolutely. Advertisements, health advice, political arguments, even casual conversations. Understanding the principles of the scientific method gives you a mental toolkit, a framework for evaluating these claims more critically.
How so? What questions can you ask?
You can ask, where did this claim come from? Is it based on careful observation or just assertion? Is the claim itself testable? What evidence is offered? Is that evidence strong or anecdotal?
Could the experiment or observation supporting it be reproduced?
Crucially, yes. And applying that other pillar, is the claim refutable? Can I even imagine an observation that would prove it false? If not, then based on the principles in our sources, you might recognize it's likely not a scientific claim, even if it sounds scientific. It might be based on belief or speculation about untestable things.
No, it helps you distinguish between different kinds of claims.
Yeah.
Those grounded in potential evidence versus those that aren't.
Precisely. It empowers you to be more discerning, to look for transparency, reproducibility, and testability, refutability. It helps you understand why evidence-based knowledge has a certain kind of reliability that might be lacking in claims based purely on authority, intuition, or dogma.
It's not just about understanding science, but about applying a similar kind of critical, evidence-focused thinking to information in general.
It provides a benchmark for what makes a claim about the natural world trustworthy. It highlights the difference between knowing something because it's been rigorously tested and verified and believing something for other reasons.
This has been a really illuminating deep dive. We've gone from the basic definition that rigorous empirical process, explored its key features like being non-dogmatic and evidence-based, walked through the practical steps from observation to thesis, and really hammered home the importance of those twin pillars: reproducibility and refutability. It paints a picture of science as a dynamic, demanding, but ultimately powerful way of knowing.
A process constantly striving for a better, more accurate understanding of the world, driven by evidence and a willingness to correct itself.
So as we finish up, here's a final thought for you to chew on, stemming directly from that crucial pillar of refutability we discussed, as presented in the source material. If a core requirement for a claim to be scientific is that it must be possible to prove it wrong with empirical evidence, how does that change the way you view claims, especially those about things we can't observe or test, for which no empirical disproof seems possible? What does that fundamental difference imply about the line between what we can potentially know through empirical investigation and what might lie in the realm of belief, faith, or pure speculation?
That's a question that really gets to the heart of how we evaluate different kinds of information in the world today.
It certainly does. Thank you so much for joining us on this deep dive into the scientific method. We hope exploring these concepts has given you some valuable tools and perspectives.